Hi, everybody. My name is Joe Johnson from Miami University, and I'll be presenting work informing computational models of perceptual and risky decision-making with EEG and individual differences. This is work done in collaboration with Robin Thomas, Lauren Davidson, Alan Collins, and Elizabeth Pettit, and supported by the Air Force Research Labs. Many of you are probably familiar with evidence accumulation models of cognition, such as the drift diffusion model that's illustrated here. For others, briefly, the model suggests evidence accumulation, shown across time on the x-axis, proceeds towards one of two options, either up or down on the y-axis here. Specifically, from a starting point z, which may be biased towards one of the options, evidence is assumed to accumulate at some average rate v towards a decision threshold or boundary a. Each of the jagged trajectories that's shown here may be one instantiation of this process, but across multiple trials, this ultimately produces a distribution of responses and response times for each option, shown in blue here for the upper response and red for the lower response. In this framework, you can interpret things like greater drift rate as stronger evidence or higher thresholds as more conservative decision making. Now, computational models based off similar principles have been successfully applied to a number of cognitive domains, including both simpler perceptual choice and more complex value-based choices. There are important differences across these two tasks, as noted here. Thus, it is important to systematically compare these two domains, but only a handful of conflicting studies have been conducted to do so. So the current project, funded by the AFRL, is ultimately seeking to understand any systematic differences in the process across a range of tasks of increasing complexity. The current experiments illustrate our approach for two well-studied tasks to serve as starting points along this task continuum. In particular, our participants had to choose from among two Gabor patches, which was the most horizontally oriented. In a second task, the same 19 participants had to select which of two outcome 50-50 gambles they would rather play for real money. These gambles had equal expected values, but varied in the spread or variance, which is commonly used to operationalize risk in decision research. Now, in both these tasks, we manipulated the difficulty based on relevant stimulus dimensions. For the perceptual task, that was the difference in the orientation between the stimuli, and for the value-based task, it was the similarity in riskiness. Finally, we recorded ongoing scalp EEG during both tasks and had participants use a link to complete an online survey after leaving the lab, where we collected several individual difference measures such as impulsivity and decision style. Now, for the EEG data, we turned to previous work which suggested that we look at central parietal positivity, or CPP, which is shown here as averaged waveforms on parietal midline channel for 17 participants. Two of them had to be removed at excess artifacts in the EEG data. Slope, amplitude, and latency were computed as derivative measures in accord with previous work on these waveforms, but no group level differences were found. Similarly, we didn't find strong results for initial analyses of something called the N200 and the LRP, or lateralized readiness potential, which have also shown up in previous work. But there are some concerns here, in particular, the time scale across these two tasks, as well as the literatures from where these measures originated. There's not a lot of consistency. And so it's hard to tell whether we're really going to be able to find things compatible across both of these tasks. Therefore, we don't have a lot of confidence in using these measures yet in the computational model. But speaking of which, for the behavioral model, we fit a drift diffusion model using the HDDM Python toolbox by Vicky et al. This allows for estimation of not only group level parameters that can reveal the importance of different conditions, but also individual parameters specific to each participant. Now, an interesting application here is that for risky choice, we need to define each response. There is no correct and incorrect option. Research suggests that the modal choice in these types of tasks is risk aversion when the expected values are equal. And so we're going to call that the correct response and develop the model accordingly. In particular, we estimated drift rates, threshold, and non-decision time as parameters, but not variability in those parameters. And we also didn't estimate a parameter for the starting bias. We estimated the model separately for each task as a baseline, and then we also estimated for each of the tasks with drift rate dependence on the task difficulty to see whether or not there was an effect of that task condition on the model parameter. Overall, indeed, we found lower drift rates and greater thresholds for risky choice, as Dutiel and Rieskamp found in 2016 paper. We also found an advantage for the models that did include the drift rate dependence on difficulty. Finally, because we have individual parameter values, we can see whether those might correlate with relevant individual difference variables. And in particular, we found that the value-based thresholds did have associations with conscientiousness, impulsivity, and avoidant decision style.